diagonalize the matrix if possible. So we got a 2 by 2 matrix. First we find its eigenvalues, okay, lambda. If we find two distinct eigenvalues, then it is diagonalizable. Sometimes we just find one, okay, with multiplicity 2. In that case, if we find just one, we then find eigenvectors. And if there are two eigenvectors, obviously linearly independent eigenvectors, then this is diagonalizable. But if we find just one eigenvector, then it is not diagonalizable. So in any case, we need to find first the eigenvalues, okay, lambda. So to find eigenvalues, we just do the following. We just solve this characteristic equation. Lambda I minus a equals 0, and lambda I means lambda times, so I is identity matrix 1 0 0 0. When we multiply by lambda, we get lambda 0 0 lambda, then minus a. So this lambda 0 0 lambda minus a is the given matrix, which is 3 negative 1 1 5. If we subtract lambda minus 3, 0 minus negative 1 positive 1, 0 minus 1 negative 1, lambda minus 5. So we have this matrix. Now determinant of this matrix, which is easy because we got a 2 by 2 matrix. So determinant is just multiply this diagonal minus diagonal elements minus this, and we set that equals 0. Okay, so determinant of lambda I minus a equals 0 implies, what is the determinant here? Lambda minus 3 times lambda minus 5 this way, minus negative 1 times 1 is negative 1, minus negative 1 means plus 1 equals 0. Now we need to solve this characteristic equation of this plus 1. If it do not here, then lambda equals 3, lambda equals 5. That would be the case, but there's a plus 1, so we need to multiply. So lambda is square minus 5 lambda minus 3 lambda 8 lambda, negative 3 times negative 5 is positive 15 plus 1 16 equals 0. Let's factor. Looks like it factors lambda minus 4 lambda minus 4, so this implies lambda equals 4 with multiplicity of 2. So we got only one eigenvalue. If we had two eigenvalues, then this would be obviously diagonalizable, because for 2 by 2 having two distinct eigenvalues suffices, okay, suffices, but it's not the case here. We got only one eigenvalue. Now we want to find corresponding eigenvectors, okay, eigenvectors. It can be 2 or 1. Next we find the corresponding eigenvectors. I don't know, maybe 1 or 2. If we get two eigenvectors, then this will be diagonalizable. If there is only one eigenvector, then no. Okay, we just solve lambda I minus a, the vector v or x doesn't matter, equals 0. So we solve this for v, where v is v1 v2 because it's just 2 by 2. So lambda I minus a is already here. Okay, so this is lambda I minus a. Now we need to put the correct value of lambda, that is 4. Lambda I minus a equals 0. We can just write the augmented matrix for that. So with correct value of lambda, so lambda is 4, so 4 minus 3, just 1, and we got 1, negative 1, so lambda is 4, right? 4 minus 5 is negative 1. That's lambda I minus a. This vector, I'm writing augmented matrix, so I just I don't have to write this, so 0 is just 0 0. So now we solve this. So v means this v is in fact vector v1 v2, and this is v1 v2. We could have written x x1 x2 x1 x2. Okay, now let's row reduce this. Negative 1 negative 1. If we add row 1 and row 2, 1 minus 1 0, 1 minus 1 0, so everything will be just 0. So this one is same as 1 1 0 0 0 0. So this is already in reduced echelon form. Okay, and here is the pivot. So this is pivot, there is no pivot, so it's like v1 v2, two components, and this is free. Okay, there is no pivot here, this is free from the first. Okay, v2 is just v2, 1 v1 plus 1 v2 equals 0, v1 plus v2 0, and v2 is just free, so this implies v1 equals negative v2. Then our vector, eigenvector, which is in fact v1 v2, which is v1 is negative v2, v2 is just free v2, and we can always get v2 out, that leaves negative 1 0, or we can pull negative outside, negative v2, that means 1, and this is negative 1. Or now this is a basis for the eigenspace corresponding to eigenvector lambda equals 4. In any case, we got eigenpair. Unfortunately only one vector, so for lambda equals 1, lambda equals 4, we got only one corresponding eigenvector. Okay, this is just one. I mean, the eigenspace is one dimensional, but this is a 2 by 2 matrix, so we need two linearly independent eigenvectors. That's not the case, so only one eigenvector. Then what is the conclusion? Not diagonalizable.